So in our last section uh, for this class, we're going to talk about Cauchy's two integral formulas and what we can learn from them. The first one is here, what is sometimes called the Cauchy integral formula. And it tells us that if we have an analytic function in a simply connected domain D and C a simple closed contour in D, then for any z naught interior to C, the value of the function at z naught is 1 over 2 pi I times a contour integral. Now, the setup is on the left-hand side here. Here we have D, uh, this blue shaded region. It's simply connected because it's connected. You can walk between any 2 points. It's open and it's not missing any points inside. We have a contour C in D right there. And we have a point z naught inside of that contour. Okay? So the Cauchy's integral formula says, hey, when you have this setup, which is very general, this is a very general setup, the value of the function at z naught is given by this contour integral, and there's an adjustment factor. There's a 1 over 2 pi I adjustment factor. That 1 over 2 pi I should look very suspicious, and or not suspicious, but familiar. And we'll see that it's actually it is in fact familiar. So we're not going to prove it, but I will sketch the proof for you. The proof is in, of course, our book. So we know that these in this situation, well, f of z is analytic, and z minus z naught is analytic away from 0. So this is analytic on d less this point, z naught. So that's great. So in particular, what that will tell us is that we can actually deform C, so we can get arbitrarily close to Z naught. So I'll call that C1. So for any deformation C of Z naught, or C1 of Z of C rather, the contour integral, the thing that we care about without the 2 pi I correction, is just the same as the contour integral over C1. And so in particular, you can assume C is a circle centered at Z naught of radius some r by the principle of deformation of contours or paths. Okay, so we know that, great. And so what we're going to do is we're going to assume, I'm going to write a capital I there. We're going to assume that it is in fact a contour integral over a circle of radius capital R centered at Z naught. And then we are going to allow ourselves to pick R as small as we want. Okay, because this R, it doesn't matter what R is, it's always the same thing. All right, so the integral then, I'm going to call it CR for the circle of radius R of f of z over z minus z naught dz is going to be the integral over CR of, I'm going to add in a 0. So we're going to add in the value of the function at z naught and subtract it off. And then we can break this up as the integral over that circle of radius R, f of z naught over z minus z naught dz, plus what's left is this portion from the numerator. And so, oops, this should be a z here. My bad. There we go. So this is what's left. And I'm going to put the negative on the other side. Great, so we have that. Now our first integral, f of z naught's a constant. It's the value of the function at z naught. So we can pull it out, and we get this familiar expression. And this other integral is the integral over CR of a difference quotient for f. dz. Okay, that's exactly a difference quotient. So it's the thing that we used to compute the derivative of f. Okay? So in particular, when r gets very small, this value approaches the value of the derivative of f. Okay? So as r goes to 0, it approaches a constant. It approaches the f prime of z naught, which exists because f is analytic. All right, so this is going to be f of z naught. This integral we've computed a bunch of times. That's 2 pi I, because it's z minus z naught to the power 1 on a circle centered at z naught. And this other guy is of size, at most, some constant times the length of CR, which is equal to constant times 2 pi r, right? Because the length of a circle of radius r is 2 pi r. Okay, so I told you this was going to be a sketch. I'm being very sketchy here. Now, as r goes to 0, the value of the contour is not going to change. It's constant. So the left-hand side stays the same. In particular, we get the integral over c, f of z over z minus z naught dz. And the right-hand side, so stays the same part. The right-hand side, well, this first portion here is a constant. So that's f of z naught times 2 pi I, plus something which has size going to 0 as capital R goes to 0. So that vanishes eventually in the limit. All right, so then we solve for f of z naught here, and we have the result. Okay, so it's not hard work, but some of the extra work is to be careful with limits and epsilons and whatnot to qualify this of size at most. But I leave that to you to read the book if you're interested in it.